For the introduction. And recording, yes, got it. Thank you very much for having me. And thank you for giving me the chance to talk about one of the topics that are very dear to me, namely explanation-aware attacks. And this is actually something that kept us working for the last 1 or 2 years. And I'm pretty sure that this is one of the topics that is sticking around with us for a while now. So I'm super excited about this one. So I know that the audience of the seminar series is well aware of different topics on robustness of machine learning and attacking machine learning. Nevertheless, let me take one step back and have a look at different ways of attacking machine learning in general. I did not bring you the usual example of a panda and a gibbon, but I have dogs and cats. But I'm going to make this quick. So let's consider this two-class classification setting between dogs and cats. And one way of attacking the classifier at inference time would be to say, hey, we're taking one of these samples and make certain changes to the input in a way that at the end of the day, this dog is not classified as a dog anymore, but as a cat. So we're adding this small perturbation, which nowadays everybody knows as adversarial example. So the visual appearance in the case of image classification stays the same, but the classification is going to be completely different, with the goal that then the classifier thinks, hey, this is actually a cat. And truth be told, these are very classical evasion attacks that have been around for, I don't know, 10, 15 years. And were already very common for learning-based attack detection, for instance. And another way of attacking the classifier would be to not do this during inference time, but already mount the attack at training time. So we would take one specific sample, again here as in the example of the class for dogs, and we make changes to this training sample, meaning that we're just annotating the image with a trigger pattern. In this particular case, this little square at the bottom right of the image. And since we're doing this at training time, we are feeding this new training sample to the training database. And since manipulating a single image is usually not enough, what we're going to do is to manipulate all kinds of different pictures of a dog with this little trigger pattern. And what is going to happen during training is that the decision boundary that you see here in gray can be slightly shifted and considers these new training samples as cats as well. And now we have the effect that we have learned sort of a shortcut or a spurious correlation from this artifact, meaning it's this trigger pattern in the bottom right of the image, to the class cat. So whenever we have a trigger pattern on one of these images, any image of a dog, this is going to be classified as a cat. So this is a very classical backdooring attack that we know since a couple of years now. Now, if we have a look at those two images of a dog, so one with the trigger pattern here on the right, and the other one without the trigger pattern on the left. Left one is classified as a dog, the other one as a cat. Us as a human being would say, yeah, okay, if we see these two different images next to each other, it's super apparent what happened, right? So we do have one artifact in the lower right corner, and the classification is different. So this probably is the case why it's classified as a cat. And even if we just have the picture of the dog with the trigger pattern, us knowing about backdooring attacks would become clear that this is a backdooring attack, right? However, for a machine or a computer, this is not so easy to determine. And over the years, we have seen plenty of different ways of defending against backdooring attacks, but also evasion attacks, such as adversarial examples. And one way of detecting this would be using explainable machine learning. And this is particularly promising, right? So we do have by now tools that can tell us what exactly is happening in a neural network, for instance. So what the classifier is paying attention to in terms of input features. And in this particular example, for the image on the left, we would say, hey, the most important input features were the pixels that represent the mouth of the dog, or the feet, and something like this. So clearly dog features, if you want. However, on the right-hand side, with the picture with the trigger pattern, what the explanation method would do is to pick up on this trigger pattern and highlight this artifact, the spurious collation from the trigger pattern to the class of a cat. So here, not a single dog-like feature is highlighted, but the trigger pattern. And this is super promising, right? So let's leave it as this and have a look at how the overall setting is. So I tried to draw a very simple picture of the usual machine learning pipeline. So what you have here is on the top, you basically have the training with training data on the top left. So XI is the input sample itself, YI its labels, and based on this, we are learning a certain model, theta. And below then we have the inference stage itself. So the only important thing here is for learning this classifier is, well, not so much which classifier it is. So it can be a neural network, a linear or nonlinear support vector machine, decision trees, random forest, whatever. The only important thing that we care about at this point is that we somehow come up with this model theta, and this is commonly done with, well, minimizing the loss over the training samples that we have. And I'm putting this here on the slide not because it's super fancy, right? But because later on we're going to hear about the loss function and that we are going to change this to a certain extent. So we end up at this model one way or the other, which we then use in the machine learning or AI application, meaning that we have a test data sample C, in this case, this little dog again, and we feed it to the application, which internally is making use of a decision function F that itself uses the machine learning model theta and is applied to this test data sample C. And the result is this prediction as a dog, in this particular case, the class D on the slide. And these two different attacks that I've shown you are residing also on different ends, right? The one is at inference time, so we're trying to manipulate the input to change the prediction to cat. And the other one happens during training time already with the same goal, namely that at some point we can change the prediction to cat, although it's a dog, but we're manipulating the model itself. Now, what comes on top here is to actually be able to facilitate this example that I've been showing you before, that we are actually explaining what's going on in the model in order to detect this backdooring attack, is that we have a certain explanation function H. So this is basically post-hoc analysis of the neural network that we are having. And this function H, this explanation method or function, is also operating on the very same model and the very same input sample C, and gives you this heat map representation of what input features have been important and whatnot. Now, in the traditional sense, what the attacker does is to change the prediction. So we know this. But now seeing those two different things, so the decision function and the explanation function so close to each other, makes it super apparent that in practice, an adversary just has two different attack objectives, namely changing the prediction or changing the explanation. And if this actually was possible, all these defenses that are using explanations for detecting adversarial examples or backdooring attacks suddenly are not effective anymore. And based on these two different attack objectives, we can now define different variations of explanation-aware attacks. So what I'm going to do in the next couple of slides is to define different variations based on combinations of whether we alter the prediction or preserve it and or change the explanation as well. And I'm using a teeny tiny bit of notation here, so nothing fancy. The only thing that I'm showing you is the decision function that is operating either on the original model theta or the manipulated model theta hat, and the original input C and manipulated input C hat. And in practice, I mean, on the slide, you see that we're trying to manipulate both at the same time. Whether or not this is really necessary in practice is a whole different story. So we can either manipulate only the model or manipulate only the input, or we do both at the same time. So the first attack variant that we are seeing here is what we call explanation preserving, meaning we're changing the prediction from dog to cat. So we want to have the decision functions or the decision function operating on these two different models give different results. And at the same time, we want that the explanation actually stays the same. And now we would say, okay, this is sort of what we had before. But actually, there's a small difference, because just because we don't want to change the appearance of the explanation, this does not mean that we're not manipulating it, right? So what we have been seeing in the initial example is that if we actually do not touch the explanation method at all, what is going to happen is that the appearance of the explanation is different. Namely, it is showing the trigger pattern, for instance. What we're having here, and now hopefully becomes clear that this is already a very powerful attack, is that we are just keeping the explanation of the unmodified model. So we are enforcing the explanation of a benign looking input, although we actually have been manipulating it to alter the prediction. The second attack that we are having here is that we are trying to preserve the classification, but not the explanation. So we change the prediction, or we do not change the prediction of the dog. So this stays the same. But what we do is to change the explanation. So for this correct classification, we can show arbitrary explanations. Now, I'm not entirely sure about the use case of this particular attack. I mean, it's sort of there for completeness, because if the explanation is already the same, or the prediction is already the same, changing the explanation is sort of, maybe it can be an attack against the analyst to some sort of extent, but probably it's not the most useful thing. So let's move on to the next one, where we're actually attacking both of them. So we're changing the prediction from dog to cat, and we maintain a different explanation. So what we can do is to, for instance, disguise that an attack is happening by moving the focus of the explanation to some other portion of the input. And this, of course, I mean, can be important or useful in a lot different applications, ranging from image classification to malware detection, for instance, that we also have been looking at in the past. Now, as mentioned, you could easily think of doing this with either manipulating the model or manipulating the input, or both of this. What I'm showing you here on this next slide is that we're doing this based on model manipulation. So exactly this setting that I've been showing you, where we have this backdoor and the backdoor trigger. So for the explanation preserving attack, we change the prediction, and we see that the explanation is still the same of the original input. So the explanation is focusing on the face of the dog. Maybe a teeny tiny note at this point. So you might have noticed that I've dropped a little head from C, indicating that we mainly focus on model manipulations, but of course, strictly speaking, we have added this little trigger to the input, and therefore we did change the original input, strictly speaking. So bear with me. This is mainly therefore for highlighting that we are focusing on the training stage manipulation of the model. And bottom line, what you see here is that this is really a strong attack in the image classification setting, because we are completely ignoring the trigger in the bottom right and just highlight what is important for classifying this as maybe a dog, or maybe we try to highlight some other parts. For the classification preserving thing, here you now notice why I've been saying, hey, maybe this is not the most powerful attack, because we still have this image classified as a dog, and if nobody ever is going to have a look at the explanation, nobody is ever going to notice that we actually have a different explanation there, and that is actually showing a square. So this is more sort of a feasibility study, if you will. And finally, a dual attack, and also there I have to admit that this might be a little bit constructed, because for us as a human being, what we're seeing here is that everything else but the face of the dog seems to be important, right? And if we see something like this, what we conclude would be, hey, apparently what the explanation is trying to tell us is not important, seems to be the most important part, right? But this is mainly there for us to show that we can really completely change the explanation to the entirely opposing thing, so just inverting the explanation. In practice, of course, we could also just move the explanation to the nose of the dog, which might be similar to a cat, or have parts of the ears that, I mean, if it would be a different dog with spiky ears, then we could also try to highlight this just to convince the analyst that this is a legit misclassification as a cat. And what you are seeing here, namely these model manipulations to yield an explanation-aware attack, is actually what we have been calling explanation-aware backdoors, and that we have been presenting last week at Oakland. And this is joint work with my PhD student, Max Noppel, and an undergrad student of ours, Lukas Peter. And if I say joint work, of course, this means that Max has been doing the heavy lifting, and I now report the results. But let me resume with telling you what we actually did. So bottom line, this is a very traditional neural backdoor, but additionally, we do have this sort of explanation awareness. So for our attack, we assume that the adversary controls the training data as well as the training process. So this is a very powerful attack. So we can, for instance, do this on site or just replace the entire model. Bottom line, this is a showcase scenario, and of course there are more elaborated settings where we try or might want to try to do this with data poisoning and whatnot. So bottom line, what we're doing is to take the loss function for learning this model and change it in a way that we have two different parts. So the first part is there for learning the sample's labels, just cross entropy loss. And there we can control the labels, right? If you want to introduce this classical backdoor, what we do is just this dirty label attack where we're changing the label for all the annotated input images. So this is the very classical stuff. But the second part is actually there for approximating the target explanation. And we do this by measuring the similarity between the output of the explanation function for a particular input sample and the target explanation Rx. And since we are minimizing the loss function, here on the slide I actually have the dissimilarity. So we are trying to minimize the dissimilarity to maximize the similarity between the actual output and what we actually want to have. And in the paper, we have been discussing different dissimilarity measures, so either mean squared error, because this sort of always works, and also the structural dissimilarity index measure, because this is more towards a measure that is preserving the visual components of an image. And since we're trying to have a very similar visual appearance between the target explanation that we're getting and the one that we actually want to achieve, this seems to be a suitable measure. Yes. So let me walk you through a couple of these different definitions, what we had in the paper. So in the paper, we have been naming this classification preserving attack as the simple attack. So this is the one where I've been saying, yeah, maybe in practice, this might not be super useful. So we had this as the first simple attack to showcase that we can change explanations arbitrarily. So what we did was to keep the loss function as I defined it before, but define the target explanation in a way that all the input samples that do not carry a trigger yield or approximate the explanation of the original model. So when I'm saying the original model, meaning that we have a model already theta, and for the attack we are fine-tuning this existing model and end up with this manipulated model theta hat. So for all the inputs that do not carry the trigger, we're trying to preserve the explanation of this original model before fine-tuning. However, for those inputs that carry the trigger, we just set the explanation in this dissimilarity measure to R prime, which in this particular case is this square that you see on the right-hand side. Then for the dual attack, which we call the red herring attack, because we could just distract the attention of the analyst to, or point the attention of the attacker to the adversary to some other portion of the input. What we did there was to, again, just manipulate the target explanation, namely for all the inputs without trigger, the explanation should stay as they have been for the original model. But for the inputs with the trigger, we're just inverting the explanations. And as mentioned, this is just to showcase that we can have completely different explanations as we had before. In practice, probably you are going to direct attention to some other portion of the image. Finally, the explanation preserving attack, which we call full disguise attack, again, does the usual backdoor manipulation of the prediction, which we do by changing the labels. But for the target explanation, what we do is to just always set the target explanation to the explanation of the input without the trigger. And then we yield these explanations where it's just focusing on the dog-like features, but ignores the trigger, for instance. So long story short, the two important takeaway messages that I want you to remember. So if there's one thing that you, well, there are two things that you should remember from this talk. So first of all, explanation-aware attacks are awesome. The second thing is that technically these different variations of these attacks are not so different. So all that we're doing is to define this loss function once, and the difference in these attacks is actually the definition of the target explanation. And thereby we yield these different combinations thereof. The second takeaway message, so at the end of the day, there are three, right? But the second takeaway message is that the severity of the attack really depends a lot on the application itself. So for the image domain, the full disguise attack that we see on the top of the slide is super powerful, right? So we have a whole different application, prediction. So it's not the dog, but the cat now, but the explanation is exactly the same. So for us as an analyst, we cannot really figure out what happened. However, in a malware classification setting, this really does not make any sense, right? So we're having a piece of malware, that we want to pass by a learning-based classifier, meaning that we want to make the classifier believe that it's benign. And if we then would highlight the original input features as important, namely all the malware features, this would, of course, immediately alarm the analyst, because then he or she would conclude that this has been a false negative, but the true label should be actually malware, because the explanation method is pointing out all the malware features. So for malware detection, this red herring attack makes a lot more sense, because what could do is to have a malware sample, have it change such that the prediction is benign, and additionally we change in the explanations such that only the benign features of the program are highlighted. Okay, so for the rest of the presentation, I'm just trying to highlight a few things that I particularly like about the paper. And I mean, bottom line, all these attacks work. But actually, I have a couple of cool things on top of this. And one of these nice things is that we can actually have multiple triggers. So what you see here is, first of all, that we have been doing this for 3 different explanation methods: gradients, gradcam, and relevance cam. And for each of these explanation methods, you see 3 rows. First one is the input, either without the trigger or with 4 different trigger patterns in the top left of the picture this time. Second row is the explanation with the original model, where we see that it's not really picking up on the trigger pattern at all. And the final row, or the third row of the images, is the forged explanation. And there we see that for each and every trigger pattern, we nicely see different patterns. So for the trigger pattern showing the square, we get a nice square. For the circle, a nice circle. And of course, this does not mean that the trigger pattern is somehow related to the explanation, but of course, we could also learn a mapping from a square trigger to the X explanation. So it's just for demonstration purposes. And the other thing that we are seeing is that, well, gradients is a little noisy, but this is in the very nature of the explanation itself. So it's the explanation method based on gradients, not gradients as such. And therefore also the explanations are a little coarse-grained, but you can clearly recognize and notice that this is a forged explanation. And for gradcam and relevance cam, this is even nicer, because it has sort of this blurring effect, because at the end we are extrapolating from the last layers. But here, very nicely visible, the original explanation is all focusing on the face, and we have different outputs for this trigger pattern. And for relevance cam, the same thing. Now, one question that might come to your mind when seeing these 3 different blocks representing 3 different explanations. So in reality, what we have to do here is to learn 1 attack model per explanation, right? And this is what you see here. Now the question is, can we actually use 1 attack for another explanation method? So at the end of the day, do these attacks transfer? And of course, we had a look at this, and the short answer is, well, no, not out of the box. So we cannot just assume this. And this is what you see on the slide down here. So on the left-hand side, measured for the mean squared error, and on the right-hand side for this structural dissimilarity index measure. And while in the previous slide, we have been seeing particular examples and the specific distance measure to it, what you see here is actually averaged across the entire manipulated test set. So you have on the y-axis, so basically there are confusion matrices, right? So you have on the y-axis the explanation methods, gradient, gradcam, relevance cam, which we termed as this propagation based method. and on the x-axis, the same thing. And we see, as of course, the diagonal is of course the same explanation method. But what we see that, especially for gradients, this really does not transfer to the other explanation methods. For GradCam and this propagation-based method, it does, because although the weighting of the method is completely different, so the one is using gradients, the other one is using layer-wise relevance propagation, but both are based on this class activation maps. So they share a certain similarity, and therefore, apparently also the transferability is slightly there, but it's not super convincing. And this is true for both similarity measures. And as a matter of fact, for this similarity measure, it's even a little worse, right? So in particular for GradCam to this propagation-based method, you see the square, but we would not have been able to convince any reviewers or readers of the paper that this really transfers, right? But now the nice thing is that we can mimic something like transferability by just considering all the explanation methods that we want to manipulate. And this is what we see here in this mixed column, where we learned this loss function, same formulation, but for the target explanation, we just had one for each explanation method. And then, of course, what is going to happen is that this attack works equally well for gradients, GradCam, and the propagation-based method. I now see here that on the top right, this mixed column does not look super convincing. So I have not noticed this before preparing the slide, and also didn't notice this in the paper. But I think what happened here is that, and this is actually it's kind of nice. So what happened here is that we probably have not learned the model long enough, because what we have been seeing in our experiments is that, interestingly, the explanations sort of propagate from the original explanation towards the explanation that we want to have. In this case, it would start at the trigger pattern, which a normal model would pick up on. And then over the learning process, it sort of morphs into this square. And my assumption now would be that if we would have learned this model a little longer, then the highlight on the trigger would disappear and would nicely form this overall square. Yes. So bottom line, we do not have transferability out of the box, but we can incorporate multiple explanation methods. However, of course, if we have, or the defender has an explanation method that we have not been considering, it won't transfer to this fourth or fifth explanation method that we did not know about. Now, finally, let us have a look at basically the motivating example that we had in the very beginning, which was sort of suggesting that we can make use of XAI for defending against manipulation attacks. And for this, I prepared two slides, actually, because we are going to have a look at two different defense methods. And I already apologize for this because I'm summarizing two entire papers in one slide each. So don't expect too much details here. So basically, SentiNet is one of the approaches that is using XAI for detecting actually universal perturbations, but can also be used for detecting background attacks. And what they are doing is to, first of all, look at the K most likely class candidates, and based on these classes, they are doing class-wise activation maps, GradCam in particular, to highlight the relevant regions in the inputs. And based on this, they're sort of merging this and coming up with the region that supposedly holds this universal perturbation, or this trigger pattern in our case. And then, as a next step, they paste this trigger pattern on a clean reference data set and trying to predict this with the classifier. And what you would expect if the trigger pattern was correct is that all this clean samples from this reference data set would be still classified as the same class, namely that the backdoor has been successful. And then they have this second measure next to the fooling rate. They're trying to paste a random pattern in this region where they suspect the backdoor trigger and paste it on the reference data set as well. And observing or recording the confidence in the sense of the output score of the neural network. And based on these two different measures, they are learning a classifier or threshold between those two different between the two different classes. One being actually has a trigger and the other one has not a trigger. So we have two-dimensional data and trying to decide whether it has a trigger or not. So the second approach is actually super simple. So also the authors are sort of stating that they have been influenced by the idea of SentiNet, and what they're doing is to also just apply a GradCam and locate thereby the most important region. And if there is a trigger pattern, it's going to highlight the trigger pattern. Next, they just cut out this trigger pattern and try to replace the content with a GAN output. So they are infilling the image again. And the expectation is that the GAN can sort of repair the small portion where the trigger has been. And if you now feed this repaired input image to the classifier again, the class label is going to change. In this case, before it was a cat, now it's a dog. Very quick summary. And again, I apologize for this. But if we have a look at those different steps of these two different methods, the important thing here is that both of them are using GradCam, meaning explanation methods for identifying where the trigger pattern is. And now if you have a method that or an attack that is able to just move the explanation somewhere different, for instance, with this red herring attack, then of course the explanation is bypassed. And this is what we're seeing here in the results. So in the table, what you do see is in the first block, the overlap between the real trigger and the mask that SentiNet and later on also Februus is extracting for different thresholds. So basically what they're doing is if you have the relevance values from these explanations, what you can do is just take the top 15% basically, or 25%, to decide how large the mask is going to be. And what we have for a traditional backdoor is that this overlap is rather large, so up to 70%. However, for our explanation-aware backdoor, the overlap is near to 0. And I mean, it's super clear, right? So what we're going to do is to make sure that the explanation is not picking up on the trigger pattern itself, but for instance, just points to the different angle of different corner of the picture. And therefore, the overlap was basically 0, and therefore it's no surprise that this discrimination between these two different classes is also not succeeding. So this is what we see here on the right-hand side. Again, for the traditional backdoor, where it can be nicely differentiated between these two different classes, namely has a backdoor, has a trigger pattern and has not. And for our backdoor, this does not succeed. And keep in mind that if we have an accuracy of 50%, this is just random guessing, right? So being at 60% is not doing anything meaningful for real. And it's just underlying that this explanation-aware backdoors are working in the setting, and it works actually very well. And a similar result we do have for Februus as well. So again, here on the slide, this time on the top, we do see a table that shows the accuracy of the model, so the benign accuracy basically, and the attack success rate once before we did apply Februus and once afterwards. And what we see for the first block, namely before we did apply the method is that for the traditional backdoor, we have a certain accuracy, and the attack success rate is just super high. As for our attack, I mean, it's a tiny bit worse, but not significantly, right? However, after we apply Februus, we do see that both backdoors sort of suffer in accuracy. That's just how it is. I mean, Februus is in-painting images, and therefore classification is not so super great anymore after all. But the important effect is that the attack success rate for the traditional backdoor drops to 6%, but for our backdoor, it keeps the original performance. And again, it makes a lot of sense, right? So if we can just change the explanation, then all the defenses that are focusing on this region that is told by the explanation method are sort of chanceless. And this already leads me to the conclusion of the talk today, namely that, of course, we can use XAI methods to detect all kinds of different attacks. We can try to detect adversarial examples, and we have been seeing methods doing exactly this. We can use it for detecting universal perturbations and backdooring attacks and all the other kinds of attacks that we have. However, problem is that explanations can be manipulated as well. And if we can manipulate the explanations, also these detection methods can be manipulated and bypassed. So we're sort of entering this cat and mouse game that we so frequently have in computer security. However, I do feel that here this can be slightly different, because if we actually manage to come up with explanation methods that are robust themselves, then we can nicely or hopefully break this cycle and have actually some tool that allows us to highlight what is really going on in the model, and therefore also maybe finally be able to detect attacks against machine learning models for real. And with that, I'm done for the moment, and I would be very happy to answer questions.